So pretty much the format of this this project, there's going to be the lecture today, and then labs are going to follow next week. I'm thinking about Wednesday night, to actually go into the lab and construct what I'm going to be talking about here. So the cost for the project, we're still kind of talking it over with IEEE if they want to sponsor it or not. So at the very most, it will be $10, but it could be less. So, okay. So the first question is, what is a headphone amplifier? So most of the times, you have an iPod, you have a CD player, you have an audio source, and you connect it directly to your headphones, right? Well, a headphone amplifier is simply an electronic device that goes in between the headphones and the iPod or the music source. The big question is, why do I need a headphone amplifier? Why can't I just plug my headphones directly into my iPod? I mean, it seems like that would make sense, right? So there's two big reasons why you would want a headphone amplifier. The first is impedance matching, which is a topic that they cover a lot in electrical engineering course, so I'll go over it real quickly here. But the second is lowering distortion. Okay. This was actually an a cartoon that I found in the State News. So you have the nerdy electrical engineer going into Best Buy and asking a sort of technical question and kind of stumping the employee. It brings up a good point. I mean, typically you buy an iPod and it comes with the white earbuds, right? Those are 32 ohm impedance headphones. And so obviously the iPod itself is designed to work well with those 32 ohm impedance headphones. But then the question is, what if you plug a different type of headphones into an iPod? Still work? Will it kind of work? Here's just kind of a general overview of the different types of impedances that you will see in audio. The biggest difference you will see between speakers and headphones is that speakers have a really low impedance, and then headphones have a really high impedance. The third bullet point there are actually measurements that I took in the lab. So you can see the Apple earbuds are pretty close to 32. The Sennheiser HD650s, those are these right here. Technically should be 300, but 286, that's pretty close to. So I guess if you're not an electrical engineer, the big question is, what is impedance? What does it mean? To simplify it, let's just talk about resistance. So pretty much the difference between the two, impedance and resistance. Resistance is just impedance at a frequency of 0 hertz, and then as you go up in frequency, then you have impedance. But at very low frequencies, you can just kind of make the approximation that, hey, impedance is pretty close to resistance. So the big formula you run into is what's called Ohm's law. It's the first one up here, V is equal to IR. So that pretty much means if you have a voltage and you have a resistor, you put a voltage across that resistor, it'll draw a set amount of current. And then if you take that formula, you rearrange it, you can solve for the second bullet there, the current, in terms of the voltage and the resistance. And then you can also solve for the resistance, which is simply voltage over current. So if you think of it conceptually, if you have a very high resistance, that means you have a lot of voltage and not a lot of current. On the other hand, if you have a low resistance, you have less voltage and more current. So it just places different demands on the amplifier that you're using for a specific application. The second formula is power. So the electrical engineering formula for power, you simply take voltage and you take current and you multiply the two, and that's your power in watts. If you take, the first one I did, you take this formula and then you plug it into here, you get power is equal to I squared times R. And then to generate this one, you take the second formula and you plug it into here, and you get power is equal to voltage squared divided by resistance. So the big thing to take away from that is that power is pretty much either the square of voltage or current, and then times the scale factor, either R or 1 over R. If you think if you have 1 volt and you double it to 2 volts, your power actually quadruples to 4 watts. Okay, so back to the original question. Instead of this is the answer that he should have given. So the experiment I did, I took my iPod Shuffle, turned it up to the highest volume it would go to, and then hooked it up to an oscilloscope, which is an instrument that we use in electrical engineering labs to measure voltage versus time. And I measured the maximum voltage that it could put out. Notice there's two numbers that I measured at the bottom here. One is the peak voltage, which is 2.3 volts, and the other is the RMS voltage, which is only about 0.3 or 0.35 volts. So the big thing to take away from that is a lot of times you'll see amplifiers listed as, I don't know, a 100-watt amplifier. You can specify power either as peak power or average power. And in practice, the average power is a lot less than the peak power. So for example, an amplifier that's 100 watts peak, it's maybe only 10 or 20 watts average. A big thing to watch out for when you're buying an amplifier is, are they talking about peak or are they talking about average power? So for this calculation, I'm talking about average power. So, actually, I guess I did peak. So I measured 2.3 volts peak to peak. Where did that number come from? Well, the battery voltage in most iPods is 3.7 volts. That's a standard lithium-ion battery. And then typically you can swing about 0.7 volts within that max of 3.7 volts. So if you take 3.7 and then minus 0.7 and minus 0.7, again, there's your 2.3 volts. You convert that to RMS voltage, and you get about 0.8 volts RMS. So that's your voltage limit coming out of the iPod. You also have a current limit, which I took to be about 20 milliamps RMS. So pretty much you have these two equations that I showed in a different slide to relate power to voltage and current and resistance. So what happens is you're pretty much limited on one end by voltage and on the other end of resistance by current. Does anybody here have a calculator? I'm going to do a quick calculation. So the assumption we're making is that we want 10 milliwatts of power into our headphones to get a good, reasonable listening volume. Okay, take 0.8, multiply it by 0.8, and then divide by 0.01. Okay, 64, that's, if you do the point, or 0.013, it comes out to about 66 ohms. So what that means is that at the high impedance range, you're limited by voltage. So if you have, say, 300 ohm headphones and you plug them directly into an iPod, it's not going to work, right? Because you need more voltage than the iPod can give you. On the other hand, so let's do this calculation. You take 0.01 and divide by 0.02, and then divide by 0.02 again. See what you get. 25. 25? There we go. So the lower limit then is determined by the maximum current. If you want to drive a low impedance load, say speakers or something, you need an amplifier that can give you a lot of current. So the question is, what determines volume? So obviously, the voltage output of your amplifier, so if you have a higher voltage, you would think you always have a higher volume, but that's not necessarily the case. What is true, though, is that volume is determined by power output. If you put a certain amount of power into a load, say headphones or speakers, then you get a certain amount of volume out. So for example, if you put a high voltage across a high impedance load, you might not get that much power. But if you take that same voltage and put it across a low impedance load, then you're going to get more power out. So the second reason I mentioned why you would want a headphone amplifier is distortion. A good amplifier, you put in a certain signal and you want the same signal out, right? You don't want it to change at all, except for you want it to be louder. Distortion is basically what happens when the output is no longer proportional to the input. And this happens, for example, when you try to ask more of an amplifier that it can give. So if you have an iPod that can only give you 2.3 volts peak out, and you try to get 5 volts out of it, then it's not going to work. So I'm going to show a bunch of plots here. If you're an electrical engineer, these will be very familiar to you. But if you're not, basically what I'm showing is two different graphs representing what they call time domain and then frequency domain. So one is a graph of voltage versus time. So if you were to plot out a sine wave, for example, it would look like this. It would kind of be oscillating back and forth. If you took that same signal and looked at it in the frequency domain, what you should see is one peak corresponding to the power level of that signal, and then at the frequency of oscillation. So pretty much a sine wave in the time domain is equal to one kind of like an impulse in the frequency domain. This is an experiment I did. I was basically looking at the output voltage, and then I was slowly ramping it up, seeing what happens. So this is 1 volt out, peak to peak. This is 3. This is 6. Looks pretty much the same, right? And then this is 9. What happened? It clipped, yeah. My battery voltage in this case was, I believe, about 9.6 volts. So I was trying to put out that. So yeah, it's 9.6 and then minus 0.7 twice. You're trying to put out more than it can. You pretty much chop off the top and the bottom of the waveforms. So you're putting in something that looks like this, and you're getting this out. That's no good. So pretty much some general observations. In these experiments, the load was, it was a 1 mega ohm, which is 10 to the 6th impedance oscilloscope probe. So it's drawing very little current. The second observation is that your output voltage can never be greater than your battery voltage. And you're always going to be able to swing within a certain range of that battery voltage. So the next thing I'm going to talk about is harmonic distortion. We saw distortion in the time domain as chopping off the top and the bottom of the waveform. If we move to the frequency domain now, what we're going to see is a single pure 1 kilohertz sine wave. Ideally, we should get the same 1 kilohertz sine wave out. But if we have distortion, we're going to get harmonics. 1 kilohertz, and then 2, and then 3, and then 4, and then 5 kilohertz. So this is what's called harmonic distortion. So this is another plot from a different instrument. This is what they call a spectrum analyzer. And this scale, the X here, is frequency, and then the Y is power. So for this, we have one peak right at 1 kilohertz, and then I have markers set up at 2, 3, 4, 5, 6, 7, and 8 kilohertz, measuring the power level of the signal that's there. And so with 1 volt out, there's basically nothing. Same thing holds for 3 volts. If you look at the amplitude at 1 kilohertz here, you can see it increases a little bit. And then we go to 6 volts, and geez, what happened? We're putting in 1 sine wave and we're getting 9 out. That doesn't make any sense. And then when we go to 9 volts, it gets even worse. Pretty much that's what happens when you try to overdrive an amplifier. The whole reason for a headphone amplifier is to prevent this from happening. So you want the signal you get out to be very similar to the signal that you put in. Okay, so that was kind of the first portion of the lecture, the more kind of general overview of what a headphone amplifier is, what it does, why would you want one. The second part of the lecture is going to actually kind of delve into schematics and circuit diagrams. This schematic up on the board here is actually the exact same one that is it's used in this amplifier. So this is the schematic that you're going to be building if you decide to build this. It looks pretty daunting at first, but it turns out if you break it up into little individual chunks, it's not so bad. We're going to start out by looking at the amplifier section. So I kind of decided to break it up into 3 different subcircuits, and then you basically take those subcircuits and you connect them to get the overall response. So the first circuit up there is a volume control. Does anybody know what a potentiometer is? All right, okay, so pretty much everybody does. So the general idea with a potentiometer is that you have a certain resistance to potentiometer, and then you have this little wiper here, which you can move back and forth. This is equivalent to pretty much 2 resistors in series. So what you can do is you can kind of adjust the ratio of these 2 resistors. So you get an adjustable voltage divider, which is essentially used to control the voltage that's going into your amplifier. So here's a simulation that I did in PSpice of the output voltage here with a given input, and then at 5 different settings of the potentiometer. So it's pretty simple. You turn up the volume, you get more voltage. You turn down the volume, you get less voltage. And then these little individual discrete steps show just different settings of the potentiometer. But it actually can be adjusted in an infinite amount of steps. It's an analog potentiometer, so you're not limited to these 5 steps. So the next circuit they have in there, it's basically a filter. Can anybody tell me what type of filter? Anybody? What's that again? Yeah. So pretty much you have a capacitor and then you have a resistor. So if you think of this as a voltage divider, your output's going to be across here, and then you have a certain ratio of this impedance to this impedance, right? And then the impedance of this capacitor, it's Z equals 1 over J omega C, where omega is 2 pi F. So pretty much what happens is as you change frequencies, the resistor for the most part stays the same. The capacitor, on the other hand, significantly changes as you go up or you go down in frequency. So if you want to just look at 2 points, say omega is very, very small. What is Z?
Very long.
Very, very big, right? So you have a really, really high resistance, and then you have a relatively low resistance. So what is your output voltage going to be at low frequencies?
Small.
Basically nothing, right? On the other hand, say omega is very, very big, so you have 1 over a big number, then your impedance is going to be small, right? So it's pretty much a short circuit. So you can think of, okay, everything that's here is getting to here, and it passes without any restriction. So what I did is I took that circuit, put it into PSpice, and did a simulation. And here's the result. The x-axis again is frequency, and then the y is voltage. So as you go up in frequency, you can see kind of, this is with 1 volt in, by the way, so you can kind of see that as you go up in frequency, everything you put in, you get out. But then at very low frequencies, you start to get this attenuation. So if you put in 2 hertz, for example, you would only get, let's see, what's that? About 0.3 volts out. So the question is, why would you want this filter in there? Does anybody know the answer? Tom?
Block DC.
Exactly. Turns out DC is very bad for headphones. It's also bad for speakers, but they're a little more robust and they can handle a little bit. Headphones, on the other hand, if you put a lot of DC into headphones, you'll basically just blow them. So this circuit, its entire purpose is to block DC. The only side effect, though, is if you look, this is 10 hertz right here, this is 20 hertz. So if you go up to here, at 20 hertz, you're getting a little bit of attenuation, so you're losing a little bit of low frequency response. Okay, so the third section, this is what makes a headphone amplifier. This is the amplifier in the entire design. If you took ECE 201, you should recognize this. You recognize it if you took 201? So it's a pretty standard amplifier schematic. If you, again, plug it into PSpice and simulate the output versus the input, this is what you get. The first thing, non-inverting, what that means is that the green line is the input here, for example, and then the red is the output. So non-inverting means that when this one is a maximum, this one is a maximum. If it's an inverting amplifier, for example, it would be switched. So when this one was maximum, this one would be all the way down here, it would be minimum.
Does that actually change the sound at all?
No. Well, it could. I mean, a lot of times in pro audio equipment, you see a little phase switch. So if you have 2 speakers that are playing the same signal, for example, you could get, and they're right next to each other, you could get cancellation or addition of the signals. And sometimes you flip that phase and it's a little better or a little worse. But in general, if you're just listening to one source, it's essentially equivalent to a phase shift, so you don't hear any difference.
Width.
Right.
with percussion sounds and things, sometimes you can hear a little bit of it, especially if you have it.
Well, if you have multiple microphones.
But they'd
right?
both be in phase though. But
Right.
you have the stereo field though, especially in the low frequency stuff, you can, I imagine that you can feel it a little bit.
Right.
I might be imagining it though. But
Well, it's, I mean, there's a reason they have that phase switch in a lot of audio equipment. That's all of the amplifier section. The next one is the power supply. So if you think about how an amplifier works, you're putting in a small signal and you're getting a much bigger signal out. So you have a little bit of power in and you get a lot of power out. So where does that extra power come from?
Batteries.
Battery, of course, yeah. You need a power supply. So this is kind of how I would divide up the power supply. In the design that we're going to be building, we're actually only using one battery. So you can also use two 9 volts in series, which just gives you more voltage swing. But it turns out for most headphones, 9 volts is plenty. Unless you have like 600 or 900 ohm headphones, then maybe I could see it. But for most cases, you wouldn't need that much voltage swing. So the first circuit, the one in this red box, we have a power switch. So the way we kind of implemented it in this design is when you turn it on, there's a little click. So that's basically switching on the battery. So when this is open, the batteries aren't drawing, or you're not drawing any current from the battery, so you don't have to keep constantly keep replacing the batteries. The other thing in here, you have an LED and then in series with a diode. It's actually a light emitting diode, so that's this little green LED here. So the reason you have the resistor in that basically limits the current going into the diode. Because if you took an LED and you put, in this case, 18 volts across it, you would fry it. So if you think of Ohm's law again, you have 18 volts, divide that by 10 k ohm.
1.8 milliamps.
1.8 milliamps. So the second, the one in the green, the amplifier circuit, I can go back to it real quick. It runs off two power supply voltages, plus 9 volts and minus 9 volts. A battery only gives you 1 voltage, so what do? Kind of the solution is you take a voltage divider, an equal voltage divider, and what you get is, in this case, 18 volts here, 9 there, and then 0 there. And so if you think of voltage, it's a difference of two voltages, right? So if you say 9 volts, what you're really saying is, well, I have 9 minus ground, or 0 volts. The trick that this circuit plays is from here to here you have 18 minus 9, which gives you 9 volts, right? That's your positive 9 volt supply. From here to here you have 0, and then you have minus 9, so you get minus 9 volts. So pretty much what you're setting up is so-called virtual ground here. So your entire ground is up at 9 volts, and then your positive supply is 18, so it's 9 above that, and then your negative supply is 0, so it's 9 below that. And the final circuit here is basically just a capacitor across each resistor. Well, the reason you use capacitors most of the time is to keep voltages from changing. So, for example, if your amplifier tried to draw more current from the positive 9 than from the negative 9, you would get an imbalance. But if you have a capacitor there, then it'll try and keep that voltage as constant as it can. For headphone amplifiers, typically, this circuit has 220 microfarads. You can use anywhere up to 470 microfarads or 1,000 microfarads. If you ever do car audio, anybody see big, huge capacitors they use in that? Yeah. When you're using speakers, it turns out your current draws a heck of a lot more, so you need these ridiculously huge, like farad-sized capacitors. But a headphone amplifier, I think this one we use 470 microfarads, which is plenty. So that concludes the lecture. Are there any questions?
What kind of op amp are you using in the amplifier?
This is a Texas Instruments op amp. It's the OPA 2132. The good thing about that specific op amp is that it's very stable. Some different op amps, when you try and plug it into the circuit, it'll oscillate, which you don't want. Anything else? All right. Well, thanks for your attention.